So I'll start straight away with some motivation here. Namely, we're looking at the Sakai equation, and this gives us an SPDE. Everybody in this audience will know that. And then we're asking about stability properties of this SPDE as a function of the sort of stochastic driving signal. And I will show or sketch that there's some rough path stability going on, and I believe this could be quite useful. And okay, so here's the hopefully familiar setting. X is some signal process, Z here is some observation process, and B and B tilde are both multidimensional prime motions assumed to be independent. Now, if sigma here, the term to the upper right-hand side, is absent, then you're in the so-called uncorrelated setting. But in general, if you want to do nonlinear filtering with correlation of the noise signals here, then this term here is present. And that has the following effect here. I'll point to that straight away. This sigma here is manifest in the first order operator here driven by Z in this gradient form here. Okay. Otherwise, the setup should be standard. G is the generator of this process here, G star the adjoint. Similar, Nj here is this first order differential operator that I wrote down here in terms of this sigma coefficients here. Either is here, and N star again the adjoint. And what happens from here to here is a switch from the Ito formulation to the Stratonovich formulation. And what you see in particular in the Ito theory, you need the stochastic parabolicity condition here, and it's simpler to look at the Stratonovich formulation. It precisely means that here you have an operator that makes the whole thing well posed, and you don't run the heat equation backwards, etc. So since G is the generator of X here, you will see a contribution of the trace of sigma times sigma transposed Hessian, and this is precisely what you take away here if you just look at the second order parts when you subtract this here. So stochastic parabolicity here is for free. Good. Now, if we take a step back here and look at the general form of this SPDE, it has this form here. It's linear in U, gradient U, Hessian U. Coefficients can depend on X, of course. And also, I want to write it in Stratonovich form for some generic first order Mj here. Now, again, in the uncorrelated case, sigma equals 0 on the previous slide, this here shrinks down to something that only depends multiplicatively on U here, and that makes life somewhat easier. And that's something I believe is very classical in the fields. I think Clark, Kushner, etc. Many sort of, this was ever since, I believe, was this observed. And what you can do in this case is you just do a smart change of variables, and you realize that you can solve this pathwise for every path Z. In fact, if you substitute for a moment here, you know, Stratonovich calculus is first order, but if you just plug in the smooth path Z here, you realize you can write this whole thing as a function of Z, and nothing happens when Z ceases to be smooth. So in fact, you can do it for every continuous path Z here. I come back to that. So let's look at this transformation because it will play a role later on. In essence, you solve the same equation here, but forget about the L. So just discard this and then stick in this particular form. This leaves you with something simple, namely a linear ODE that is parameterized by X, and of course it depends on Z, so no surprise you can solve this explicitly. Here's the solution here, and since eta does not depend on anything, just X is a constant here, pulls out here, and you see Z integrates up, so only ZT comes into play, and that makes sense for every Z continuous, right? So now we make the following transformation, and I will call it auto transform. This is a language I will sort of use later on. There will be an inner transform, etc. So just define V as implicitly in that form, or you solve it explicitly, and then V just becomes U with this sort of exponential damping here, And at least if Z is a smooth path, or if you're in some first order Stratonowicz calculus setting, you use the chain rule here and you convince yourself that dV itself satisfies again a linear PDE, and the effect of this is precisely to kill off this term here. So you switched from an SPDE to a random PDE if you want. At the end of the day, you unwrap this change of coordinates and you have constructed your robust version. Now, a benefit of this construction, as I mentioned already, is you get this in a fully pathwise sense. So the solution here will be continuous with respect to the uniform metric. That means if you stick in two paths Z, you may assume for the moment C1 so that it makes sense. If the uniformly closed, then the solution is closed. And of course, if that happens uniformly and uniform unbounded sets, etc., there's a unique extension here to every continuous path Z. So the situation is different when there is correlation. So if sigma is not 0, then this sort of trivial trick here does not work. In fact, I want to emphasize that you can't expect this result to hold. So if you look at an SPDE of this type here, or for the matter of sake, let's think of the PDE where Z is a smooth, signal of time, set C1 say, then you cannot hope for a solution U that depends continuously in uniform topology on this input signal C1. Why? Well, take L equals 0, take this one just a transport equation, so du times sigma x or so, then the solution is given by the method of stochastic characteristics. There's no crossing of the characteristics, so you have to construct a global solution by solving some auxiliary stochastic differential equation that depend on these coefficients here. And of course, stochastic differential equations do not depend continuously on the driving signal unless you have a very specific setting like commuting vector fields or something like this, but that's definitely not the case here. There's a typo, there should be a little j here, okay? Multidimensional situation. And where I'm heading to here is to the result that while this is not true in uniform topology, it is true in rough path sense. So more precisely, if you take a sequence of smooth path, if you want smooth approximation to Brownian motion, and if you can check that this is Cauchy in rough path metric, but I will be a little bit more specific later, then you can assert that the corresponding solutions to replace Z by Zn, and that gives you a Un, and you solve it in a reasonable function space so that you have uniqueness existence, etc., subject to the right conditions, of course. Then Un will converge to a limit U that depends only on this rough path limit of the sequence here. This convergence is local uniformly, etc. And again, we'll talk about this rough path stuff in a second here, but the notation is if Z is close to Z tilde and the iterated integrals of Z are close to those of Z tilde, then U is close to U tilde. And of course, it's perfectly possible to construct paths Z and Z tilde that close uniformly, but the iterated integrals that corresponds geometrically to an area that they wipe out, there's no need for them to be close, right? You can spin around and cook up differences and errors as much as you wish. Okay, so that was the brief sketch of what we are going to do, and I feel like I should speak a little bit about rough paths here. So let's forget about PDEs and SPDEs and look at ODEs, okay? So X here is now a driving signal, so smooth enough for everything to make sense what's going to come here. So this dx here is a x dot dt if you wish, and here is a ODE. The assumptions on the vector fields are such that this all makes sense here, in particular some of the estimates later. Now numerically what you can do is you do the Euler scheme, and that sort of will tell you how you can do a small step on a computer. You can iterate that, you can prove convergence and all sort of things. And if you want to go bigger time steps, then it may be a good idea to go a little bit further here. So based on a Taylor expansion using this ODE structure here, you convince yourself that a better approximation, a second order approximation here, is the first order one plus something that has to do, no surprise, with the iterated integrals of the driving signal, right? And here, just to clarify this notation here, vi, vj, really this vi is, you should read it as a directional derivative acting on vj here. So you could add another index k here and a little partial k in between, but I hope this notation here is reasonably standard. And again, here you see these iterated integrals of the driving signals popping up, and this is a better approximation, a step 2 approximation, say, and let's give it a name. Let's call it script E. Depends on your starting point here, ys, and then it depends on the increment of the driving signal plus the iterated integrals of the driving signal over sort of the simplex over the interval st. Right? So just for bookkeeping, let's put these two pieces together in one space. And let's call it some generalized increment, bold x st. So now let's make a scaling assumption here, because I want some estimates, some uniform estimates. The scaling assumption I want is of Hölder type. So I will say the path itself has Hölder scaling with exponent alpha. Well, under the assumption that you have C1, of course, this holds true with alpha equals 1, and there's nothing else to say. But I want uniform estimates, so x will not stay C1 for long. In addition, we put in the assumption here that the iterated integrals also have a scaling of Hölder type, and observe the square root here. In the Lipschitz case, that's obviously okay. If x scales like, has Lipschitz scaling, the iterated integrals here is of order t minus s square, and this 1/2 takes the square off, and you're back to t minus s to the power 1. So, surely holds true for alpha equals 1 in that setting here. And now we make the assumption it holds true for some alpha between 0 and 1. In fact, I will want it to be greater than 1/3 here in a second. And the interesting thing is this will be okay for some random constant here in the Brownian motion setting. In this case here, you will read these as iterated stochastic integrals, and you need to do some Kolmogorov or Garcia-Rodamich-Ramsey type regularity theorems to show this, but it's true. So here's the error estimate that I want to put forward. It's proved by Sandy Davy, and it's sort of the quickest way that I know of to explain rough path theory. So the statement is this: assume the previous estimate was alpha greater than 1/3. Then you have the following error estimate for the step 2 Euler scheme, right? It's just one step. If you want to prove convergence of the scheme where you iterate, then you need to do some more work. This is just for one step, okay? So if you start at ys and you look at the correct solution, remember it's all about ODEs here, and you look at the real increment and you want to approximate it with your second order Euler step, then you're doing pretty well. Namely, you're getting an estimate of delta t to the power something greater than 1. In fact, this theta has 3 alpha, and now you see this assumption 1/3, coming in here. Good. The interesting thing on this estimate is that this holds with a constant C2 that only depends on C1. And I recall C1 was this constant here. So it doesn't blow up if x ceases to be smooth. As long as you have uniform control over these guys here, you're in business. So C2 is only a function of C1. You don't lose control when things get a little rougher. On the other hand, under this generalized Hölder assumption, the previous slide, it's clear that your Euler increment itself, that was sort of manifestly defined in terms of these first 2 increments, that you have here a scaling of the estimate delta t to the power alpha. That's clear. Now plug the two together, triangle inequality. What you get is that your solution here is alpha Hölder. Okay? Well, again, we're in an ODE setting. The solution will be smooth here, or C1, but uniformity is the catch. So once you have uniformity, you exploit them, and you exploit them in the obvious way, namely, you take a whole sequence of smooth paths, and you impose uniform control of this type. Okay? And you also impose that these xn's plus the iterated integrals here converge, say pointwise, to some limiting object, a path that has a bigger state space. It's not in RD anymore, but it lives in this RD plus RD cross D. Remember, this was of the space where you put in the iterated integrals. In fact, you live in a slightly smaller space due to the algebraic relations that live in here, but let's not go into that. This is good enough. Now, definition, every object that you pick up in that way here, called a geometric graph path. Okay? Davis lemma tells us what? It says this sequence of ODE solution that we constructed is uniformly Hölder continuous. Well, boundedness is no problem. Außer-Lascoli tells you you have compactness, you have limit points. And then, if it makes you happy, you call them RDE solutions. That stands for rough differential equation. Okay? If you don't like this limit point definition, if you want some intrinsic definition, there is. Okay? But this is quicker to talk about. More regularity and a bit work. There's not one limit point. There's not just existence. There's one. Okay? So if you take any geometric graph path here, and there's precisely one RDE solution, and then you may write dy equals v of y dx, where you think of this as a proper geometric graph path. Again, there's some intrinsic definition. Now, you have constructed the map that takes a geometric graph path, and on the other hand comes out some solution, at least to this formal rough differential equation. And the map here that goes from the input to the output, let's call it the Ito-Lyons map. Rough path theory is due to Terry Lyons, as many will know. And this map is moreover continuous in many good ways. So there's a proper metric on rough path space, etc. And the solution map is locally Lipschitz. So it's all understood here. Now, this was just the step 2 story. You may expect by doing Taylor expansion not to level 2, but to any level. There's a general story. There is. And what's more important for today's talk is that here, this continuity, you don't get it only on the level sort of some uniform topology here in path space, but you get it on the level of flows of diffeomorphisms. That means it converges. If you keep the starting point open as a flow, you have local convergence here, so local uniformly with respect to the starting point. The derivatives will converge. If you look at the inverse of the flow of diffeomorphisms, there too you have convergence, the derivatives converge. So if you put in the correct assumptions on V here and optimal conditions are known, then you really have continuity of the solution map on the level of flows of diffeomorphisms, and that will be crucial for later. If you have not seen rough differential equations before, let me sort of run over this example here that gives some intuition. Here's a somewhat non-trivial rough path, namely it corresponds to the trivial path 0 in the plane that does nothing, but on this level of iterated integrals, you sort of hardwire this non-trivial t minus t behavior. And what it corresponds to is, if you remember our construction of rough paths, it corresponds to this sequence of approximations. So what does it do? You spin around the origin very quickly, namely of speed proportional to n square. You scale down at rate 1 over n. So of course uniformly you go to 0, but the level of iterated integrals, the antisymmetric part here corresponds geometrically to the area. It does not disappear, right? Every time you run around, you pick up area 1 over n square. Multiplicity times n square does not go away. So this is what you pick up in the limit. And so it makes sense to stick this abstract rough path in this abstract machinery and do something. But what is it? What does it mean? And the answer is it models the effective behavior of these approximations here. So from our approach that I've given, this is clear. So the effective behavior of these differential equations driven by these highly oscillatory input signals, and no surprise, what you converge to is the solution of the ODE driven by the lead bracket vector field V1, V2. So here understand that V is a collection of two vector fields V1, V2. So it has, in many cases, a very precise, concrete interpretation. The next interpretation I want to give is the one of the stochastic differential equation. So Brown in motion is obviously not smooth enough to solve this as an ODE, but what you can do is you can use Ito integration or Stratonovich integration and cook up these iterated integrals. In fact, I want to use Stratonovich because we're sort of we're taking limits from ODE, so it's natural that you end up with a Stratonovich theory. So either way, define this, and then it's a theorem, Kolmogorov type, with probability 1, this object here has the correct regularity that makes it a geometric graph path. In fact, you can also show that piecewise linear approximations here will converge in the good sense, and everything is understood. So in particular, if you combine this statement here, piecewise linear approximations converge in the rough path sense to this guy here. If you put it together with the well-known Wang-Tzu-Kai theorem, it tells you that this abstract rough differential equation, where you take this sort of Brownian motion plus iterated integrals as an input signal, it must coincide with the Stratonovich solution. In fact, it gives you a very nice version of the solution in the hand, where you solve it on one set of full measure for all coefficients at the same time. So I'm just trying to give some evidence that this is useful or has been used, but let's head towards the goal of this lecture here. First, I want to put this in context with Wang-Tzu-Kai here. So here's the Wang-Tzu-Kai statement. I already sketched the proof here. Well, I mean, you use this to identify the rough path solutions driven by Brownian motion and iterated integrals. Now, there's some robustness issue here that I want to highlight. Namely, it's not just that any approximation to Brownian motion uniform topology would converge here. In fact, and that comes back to the robustness condition of the beginning here, if you sort of do it in the wrong way, or if you twist it in some special way, you can see all sort of counterexamples. I mean, it is a theorem, it's correct as it stands, but you can construct uniform approximation where the limit is not what you see in the Wang-Tzu-Kai theorem. What you can do is, by spinning around in the right way, you can cook up limiting behavior that has additional leap bracket vector fields, drift vector fields coming in. Again, not a surprise if you remember our discussion of the homogenization type result. So I don't want to talk too much about this one. This is just a little theorem that says that this Wang-Tzu-Kai and McShane construction sort of just a tip of an iceberg, and there's a very generic version of that. Whatever iterated leap bracket you may pick, you can construct approximations to Brownian motion only depend on Brownian paths that you will pick up this drift vector field that lives in the least span. So in fact, McShane and the versions that you find in Ikeda Watanabe, they only tell you something about the first leap bracket coming in, but you can pick it up at any level. So Sussman knew that already by stochastic techniques. Okay. So now SPDEs. The toolbox I want to use is viscosity theory, and I will explain why. So although it seems like you're using heavy machinery to deal with ultimately linear equations, I want to insist that the techniques I present are quite usable, quite useful for nonlinear equations as well. Okay, what's viscosity theory? I want to look at some second-order parabolic setting. So f can depend on time, x, gradient, Hessian, can also depend on u itself. Okay, you have certain conditions. Sort of there is some properness condition here, and there's some condition on the monotonicity in the Hessian, which rules out basically that you run the heat equation backwards in time. But subject to some technical conditions here, there is a very clean theory, and if you do it in book space, and let's do that, then it tells you that the Cauchy problem is very well posed, so in the sense that it satisfies comparison. What it means is, if you take a sub-solution in viscosity sense, and I'm not going to define it, if it's a smooth solution, it means you plug it in and this holds us an inequality. And you take a super solution in viscosity sense, and you have compatible initial data in that sense here, then you get this inequality all over the place. Okay, this is comparison. It's very useful. If you add some bounds, then you get existence from it. It gives you immediately uniqueness. So it's a key. It's the key result in sort of viscosity theory. That's what you have to work for to get comparison. Now, the definition of viscosity solution has many advantages. So you never have to worry too much about the derivatives. If you want to pass through the limit in a sort of classical PDE, you have to control somehow the derivatives and the second derivatives. But in the viscosity framework, there are very soft results. So for instance, if you know that the sequence of solution u epsilon converges uniformly, and these f epsilons here as a function of 1, 2, 3, 4 variables converge locally uniformly, then you already know that the limit of this u epsilon will be a viscosity sub or super solution of the limiting equation. The downside of the theorem I just gave you in words is that you don't know a priori that u epsilon converges, or in many applications you have to put in work to do that. So there's a very useful version of this due to Bars and Bertam that tells you don't need to know that these u epsilon are actually locally convergent. If you just assume that they are locally bounded here, and you know that each u epsilon is a subsolution to this parabolic equation, and you know that this f epsilon converges to f, again as a function of 1, 2, 3, 4 variables, or 5 if you look at the slightly more general setup, then the so-called semi-relaxed upper limit is also a subsolution. There's the equivalent statement here for super solutions. I'm not going to write it down. So this is a very useful technique. So if you stick for a moment with the nonlinear setting, then the ultimate aim would be to do something like this: fully nonlinear here, fully nonlinear here. At present, I believe that's well out of range, but nonetheless, there's a very non-trivial result from 2003 that tells you if you delete x here, delete u here, and you look something like this here, then actually this makes sense, and it makes sense in a very sort of pathwise way, right? Which, even in comparison to SDE theory, will be surprising, because it says, look at smooth driving signals, Zn. They're all smooth enough so that each equation here, if you put the correct assumptions on f and h, makes sense, has this unique viscosity solution in book space A. So, statement is, if this Zn converge uniformly to some z which does not need to be differentiable or continuously differentiable, then these solutions here will converge to a limit, and this limit in fact depends only on z, right? So in particular, this Zn would do crazy things on the level of the area. You wouldn't see it here. So implicit here, the absence of x means there's some strong commutativity built in, but even so, the nonlinear dependence on the gradient here is a highly non-trivial thing to deal with. So this is the interpretation, or the short version of this Lyons-Souganidis result on fully nonlinear SPDEs. Applies trivially to Brown motion just by fixing a continuous path. Now, here's a sort of a rough pass version of that. It's much simpler in the sense that we have linear dependency in the gradient. On the other hand, it has x dependence built in, and in presence of x dependence, just think of the transport equation, the previous result would not possibly be true. So if Zn just converges uniformly, you say nothing about the limit. So the right thing to do is to look at the rough pass version of this. So you try to make sense out of this equation here. With some x dependence, here you stick in a rough pass. So what's the statement? Fix some bounded uniformly continuous initial data, look at the sequence of smooth functions, and assume that they converge in rough path sense to some rough path limit, which we call z bold. Okay? And then the approximate problems here are the conditions that guarantee unique viscosity solutions, but this is a standard setting here. You have convergence locally uniformly to something. This something depends only on this rough path limit z and not how you approximate it, and so it gives you the canonical way of talking about the solution to this rough partial differential equations. Again, you can cook up somehow more intrinsic formulations of what it means to be a solution here. Now, this is the remarks I made here. With x dependence, a pathwise SPDE theory must be rough pathwise. Well, it can't be. I mean, there is no pathwise theory in a general setting for SDE, so how could it be SPDEs? And of course, that's what I said. Well, perhaps I should stay 1 second on the slide here. So if you were to hope for a pathwise theory, then indeed you could cook up all sort of examples with spinning errors, etc., and pick up things in limit. So you don't want that. And that sort of justifies this assumption that you want this convergence of the approximating driving signals in rough path sense. So that's all I'm saying here, and I hope from the previous discussions this is now well motivated. Now, our h here is linear in the gradient, okay, and basically, the assumption that these set ends converge in rough path sense will tell you that the solutions to these approximate problems, so now we're talking about ODEs here, will converge to the solution of this RDE, this rough differential equation. And moreover, this will happen on the level of flows of diffeomorphisms, right? If you call psi n the flow of diffeomorphisms associated to this equation and psi the one associated to this here, this will, you have convergence here, locally uniform and starting point. The tangent flow here will converge. If you look at the inverse, the gradient, the inverse flow will also converge, etc. So why is it useful? Well, let's look. First, we make a transformation of the state space. So this goes back many years, Tubarão and Kunita, and so this is the idea of changing variables in a smart way is by no means novel here. So we define Vn to be Un viewed in different coordinates. Okay, let's call it the inner change of variables, the inner transform. And what does it do for you? Well, if you do some calculus here, then you see that the equation here, right? So here's the equation you're interested in, at least the approximations to it. Here's the noise term, at least the approximations to them. And this transformation will exactly get rid of the noise term here, okay, thanks to this du term. So this is like you add a little transport flavor to the whole thing that will kill it off, okay? And for Vn, you get a new equation here, again parabolic, but your f has changed, not surprisingly. And if you want to know how precisely it changes, well, you have this, flow of these diffeomorphisms. So it's basically the same change that you do if you write the Laplace operator in polar coordinates. That's more or less what's going on here. So the f psi here, if you want, has this form here. So you can write it out. This is trivial. The x, this is just the new x in the new coordinates reads psi t of x. R here, so it's slightly more general here. Don't worry about it. P corresponds to the gradient. Now it's the sort of push forward under the inverse flow here. And then on the second level, it's getting a little bit more complicated. It just means that that second order differential operators don't transform in a tensorial way, so you get some correction terms in here, but it's all explicit. It's no problem. So again, these transformations, you find them even in Kunita's book, for instance, in the linear setting. Good. So how is it useful for us? The useful thing is that these psi n's here, so you can take every psi here could be a psi n, and if you let n tend to infinity, these psi n's tend to psi the flow of the rough differential equation. So the gradient here, inverse flow, not a problem. All these objects here converge, right? So what you see is that Fn here, right? These are the flows that you pick up here, correspond to the diffeomorphism psi n. This will converge locally uniformly, and the limiting f is precisely the one that corresponds to f transformed with the psi that you get from this rough differential equation. Right. So now assume local boundedness of these Vn's. Make it an assumption here, but in concrete situations you just use comparison and some knowledge of your equation to verify this. So this local boundedness here is a soft condition, it's not a problem. Then you're in a position to apply the stability result. So the stability result of Bertram that I mentioned tells you what? It tells you that each Vn here is a solution to this problem. So let's say viscosity solution. So it means it's a viscosity subsolution and a viscosity supersolution. And in particular, it means that since they're subsolutions, that this upper semi-relaxed limit is also a subsolution. That's what we are seeing here. So this upper semi-relaxed limit is a subsolution to the limiting equation. It's precisely what we wrote here. On the other hand, you take the dual formulation of the stability result in terms of the lim inf, the semi-relaxed lim inf, the same story with super solutions, and that's the other side, right? Now, from the definition of these lim subs and lim inf, it's clear that this one is less equal than this one. If you now use the fact that you know comparison for this limiting equation here, it tells you precisely that all these here must coincide, that the Vn must converge to V locally uniformly. So the lim inf must be the lim sup, but therefore it must be the lim, and then some dini argument gives you locally uniform convergence. And the limit here satisfies this limiting equation. So Ball-Bertam technique in action. Then, of course, you can unwrap the change of coordinates and define what you mean by a solution to this rough differential equation. Or if you wish, you leave it in the previous form and just define a solution to this guy that it solves the transformed equation. That's a perfectly good definition, gives the existence uniqueness. So emphasize the u that you picked up here is the limit of these approximating problems, and it does not depend on how you approximate this driving rough path. It only depends on this rough path z in its intrinsic sense. Okay, well, the moral of this rather short discussion is that stability properties of viscosity theory and sort of rough path theory, in particular the discussion of flows of rough differential equations, they work together quite nicely. Applications, pathwise, rough pathwise, right? So z here must be some rough path, so in a Brownian context you take it b at the iterative integrals. Okay. What you obtain is, of course, some Stratonovich formulation, and there's no need for a stochastic probabilistic assumption here. I mean, you started with a Stratonovich setting. The assumption you need from the very beginning here is that this f that you start with needs to be, monotone in the right direction in the Hessian here, but it could be fully degenerate, right? So no strict ellipticity assumption needed here. And then it's some immediate check here that the transformed f has still these properties. Right. So that was the story where you deal with linear noise, sort of multiplicative in the gradient of u. Now the next interesting question is, how about things that also depend on u? In particular, in the filtering story, that's definitely what you need and want. Well, let's not do everything at once here. Of course, everything nonlinear would be nice, but let's do something practical from the filtering point of view and stick with the linear situation. So L here should be linear. It means linear in u, or affine linear in u, du, Hessian u. And if you look at the analysis, if you have some mild semilinearity, it's just linear in this guy. The coefficients may depend on x in nonlinear way, of course, and t, and some function in this one. Some semilinear story works immediately. Right. So what you would like is to carry out a similar program for this equation here. Okay. So again, you would like that for any smooth approximation of some genuine rough path here. So ignore this p rough path. These rough path metrics come with a hierarchy where you can sort of play around with the regularity. P is 2 plus epsilon in the Brownian setting. Right. So what's the plan here? Well, again, replace z by smooth approximations, so by zn, and then do some analysis on these approximate equations and see what you can get. What you get is that this works the same way as the previous construction worked, and also get the continuity that also holds in the previous setting that we had. So perhaps a word to the topologies here. U0 is in book space, so you put on a topology of locally uniform convergence. Z here lives in a rough path space, so that becomes a Polish space under the rough path metric, which I don't want to write down. And you said that the solution here lives again in book space, but now in time 0t cross Rn. So again, you put locally uniform convergence on it as a topology. So good. So useful, but we can't talk about that later. Idea of proof. So the first thing is, just for notation here, let me take z smooth, otherwise you make sense out of it in the rough path setting. It's just a notation here. So I want to write my m's here. I know they split up sort of linearly in something depending on u and du. I want to take it apart in this way. Okay, so there's no loss in generality of writing it in that way. If I should add, you can add if there's some term, some additive term that doesn't depend on u, that works as well. And in the paper, it's written that way. So the first thing is we get rid of this noise term, and the same technique works. We do this inner transform. You introduce some transport feature, and that will move this term just away, right? So psi here is the solution flow to the equation that's driven by this noise bit here, and then if you change coordinates and you think you introduce w is u in this new coordinates here, then it will just move this part away, and what you're left with is the initial L. So what the equation here was of the form, there was an L here on the left hand side, so that will be transformed and it becomes an L psi in the same way as here, but now it's simple because everything is linear. And what does not go away is this guy here that sticks around. And what happens also is this x, right, doesn't remain x. This x becomes psi t of x, right, corresponding to the change here. Now, we'll see it's not bad, but it's not good in the sense that you can't use this robustification trick anymore. The noise that you remain with has not the feature that here is something doesn't depend on x, and you can just solve this auxiliary ODE and integrate it all up. It's not true. So the effect of the first transformation, you can't ignore it when you do the second one. So even so, you can proceed by the same idea and look at the solution flow of the problem that just looks at the evolution of this noise term here. So it means replace w here by phi, then you have phi dot equals phi, and then this is a shorthand notation, eta of psi d theta. Right. So that's not bad. Phi here is, as a solution flow, it lives on the real line. It's nothing complicated. So if you want, you can divide this phi here off and then look at the logarithm. It's a linear equation at the end of the day. But once you look at the logarithm and integrate it up, you will see if you look at the integral of this, then it's not an integral you can just write down or integrate it up, because you have to integrate something rough against something rough, right? If this is something of diffusion regularity and this too, then there's no canonical way of cooking up these integrals. So what you have to do is you have to understand these two guys. This here is a function of t, and this is a function of t. You have to understand them together as a rough bars. So you need to understand the integrals, which is cheap enough, because if you remember where everything comes from here, this psi here, we got it in the first step by solving this equation here, right? So rough bar theory tells us we can understand this here as a rough bars. We can also understand it as a rough bars jointly with the input signal. That just means in plain language, you understand the iterated integrals of psi and this iterated integrals. If you add this theta here in this evolution here, you can understand the cross integrals between psi and theta. The only condition is you need to understand this psi and theta. You need to understand the pair here as a rough bars, which is precisely the assumption we started with. So you're in good shape. That means we can construct this one in a rough bar sense. That means with all the stability properties. And now we can sort of proceed like in the beginning. Namely, we do another change of variables. Namely, we switch from w to our final state, namely v. And, well, this is the right change of coordinates here. Since psi here is linear, it will be the starting point times something. So this psi minus 1 just means you divide by this something, which happens to be e to the some rough integral. So you do that, you end up with this transformed equation. So L psi was a transformation of the original L linear in this form that remains linear. This phi here, this outer transformed after the inner transformed, also leaves you in the class of linear L's. So that changes dramatically when you start to do something nonlinear here. And you are good. That means after two changes of coordinates, one outer, one inner one, you're left with a solution with a v that's a solution to this PDE. Of course, all these flows here depend on our little z here. So if you want to think as a probabilist, you went from the SPDE to some random PDE, and if you think in our context here, you went from some time-dependent, or from some PDE with some possibly rough noise to something where there's no more rough noise at all. Instead, you have coefficients that depend on the flow of the rough differential equation and the derivatives, but these are nice objects. Moreover, you have the stability properties that we talked about, namely, if we let our Zn, so now think here Zn, if we let Zn converge in rough path sense, all these flows here will converge, right? That means we have again locally uniform convergence of these approximations here to the one that corresponds to the limiting equation, and the same argument that I gave before, namely the Spiral-Bertam method, will tell you that you have convergence to so you have convergence, and you can characterize the limit as the solution to this limiting equation here. So now all this transformation here is, I mean, there's a very general principle here. You do this inner transform, you do this outer transform. It's all calculus. If you're in a viscosity setting, you have to write down a little bit more details, etc. You know, you can do it with subjets, superjets, or the definition here. But in essence, you know, changing coordinates is just calculus. What is not calculus is to understand that the limiting, or that the final transformed equation here satisfies comparison, right? Here, in this first setting here, when f is full and nonlinear, in our paper we made an assumption, and then we checked this assumption works in many cases, including quasi-linear operators and Bellman time operators. So here too you could make an assumption and say, well, I just assume that my final transformed equation satisfies comparison in the viscosity sense, and then the Spiral-Bertam procedure will work and tell you that there's a meaningful sort of rough partial differential equation. Now, how to check this comparison in concrete examples, that can be difficult. Now, what I said here is, in this linear setting, you're basically on good grounds. The next step is assume something, so erase the gradient here, Txu, that will still, so the technique will still apply, but now you definitely, even if f is linear, you fall out of the class of linear equations after the transformation. In fact, what you will see is that you will end up with a parabolic equation that has a quadratic term in the gradient, and sort of comparison result for such an equation is actually a pretty hard piece, but there are some results in the literature by, among others, Lian-Sogonis 2000. There was something similar, but that's still sort of a little bit in progress. What this technique will not give is a story that makes nonlinear dependence in du. So we are relying here on global transformations. But again, there are reasons to believe that there's a meaningful theory for this. Can be localized, but this is very much in the future. I want to come quickly back to the question, what is this good for? Well, the class of SPDEs we can handle with that technique is a fairly general class of linear SPDEs, linear noise. So if you're interested in things like support theorems or large deviations for small noise, or general approximation theorems a la, you know, Wong-Sakai or variations of this, but also splitting methods and maximum principles, then it's sort of this continuity results. They're very powerful techniques to get these. So the applications here, I think this is still in development, and I'm sort of excited to discuss. So I should stop here. Thank you.
Questions? Can you deal with the space-time noise?
Well, in this setting, the noise was finite dimensional. If you look at, you know, the Soviet article by Professor Krylov, for instance, you know, there are theorems that allow you to approximate space-time white noise by finite dimensional things. So if the change of coordinates works, then, you know, if this flow technique works, in principle, you can have infinitely many terms, but you probably need strong conditions on the convergence of these. So I would say it's something to be looked at.
Other questions?
Can you show again the form, the exact form for M?
M.
Yeah.
Oh, this here?
Yeah.
The most general form that you can have is that the form M here is, so M is a collection of M1 to MD, right? Matching the dimension of your driving rough path here. And every MJ here has the form. So acting on some mu sigma jx. Then there's a term multiplicative in u. So let's say u times ether x, and let's make it j here, right? And then there could be a constant term plus something plus a of x. You can put t dependence in as well if it's nice. Yeah.
So I thought that you had some sort of different noises driving the different. Maybe
Well,
I misunderstood that part.
Okay, if you understand this, so there's no loss of generality to write out the term driven. So if you drive these guys by some dz component j, right, I can split it apart.
So the two noises can be the same.
Yes, absolutely.
Short question. What is smoothness of your operator coefficients?
That's a good question. One should make a systematic comparison. The smoothness assumption for L are fairly soft because you're in the framework of viscosity theory. Now, of course, you have a the reason I like viscosity theory in that framework is because it gives me this technique of stability. Okay? But once you have transformed the equation, you can solve it in any sense you want. You can solve it in Helder sense or in Sobolev sense. That will tell you something about the spatial regularity of a solution if you do that.
But still second order derivatives of phi appear there.
Yes, but see, here, this comes from a noise part. So for the time being, I spoke about L. So here I compare various, you know, if you're happy with book solutions, then we're as general as viscosity theory allows it to be. Now the assumption here, of course, much harsher. What you need is up to two derivatives of the flow here. So what you have is, if you subsize the solution to a rough differential equation, okay, the regularity here is, the Brownian regularity is some 2 plus epsilon variation regularity. So rough path theory tells you you need lib gamma for gamma greater than p. To translate it in our setting here, you need more, but I'll come to that. So just to make sense out of an RDE, so RDE driven by a 2 plus epsilon bar rough path, and Brownian motion force in this class needs lib gamma, where gamma is greater than p, and therefore you can choose it as close to 2 as you want. Okay, so if you have lib 2 plus a little bit, where you should stop?
Sorry.
Okay, lib 4. Okay.
Thank you very much again.